Today we start chapter 9 with a section 9.1 sequences. So let's define first what sequences are. So definition. Sequence A(n) when n belongs to n is a function A mapping natural numbers n into real numbers. The value A of n is usually labeled as A. So here's an example. Let's consider the following sequence. 1 over 2 to the n when n belongs to n. Let me just mention, I assume that you all know what the natural numbers are. So n stands for numbers 1, 2, 3, 4, 5, and so on, positive integers, or sometimes also 0, 1, 2, 3, 4. So, we think of n both these different ways. So generally, sometimes we'll start with the index. So number n is actually index, and then 1 over 2 to the n is the value. So generally, how do we understand this? So we read the indexes, let's say n equals 1, of course, so n equals 1, n equals 2, n equals 3. So that's n equals 1 says, I will calculate the first member, and then the value is 1 over 2 to the 1, which is 1/2. Here is 1 over 2 squared, which is 1/4. 1 over 2 cubed equals 1 over 8. So here is the index, or you can say the rank of a member. And then here is the value of the member. All right. So the most interesting thing for us is to define the limit of a sequence. So definition. In the notes, in the textbook, you can find the formal definition, the one from the epsilon delta arsenal. But since probably you didn't see that one in your calculus 1, then I will not use that definition. So here's the question. So question is, what does it mean that limit an when n goes to infinity equals to L? As I said, I'm not going to give you epsilon delta definition because that might be a little too challenging, although that would be a real definition. So I will give you a very informal definition. So that means, so here is obviously not a very precise statement. When n is big, and that's a question of what big means because that's relative, then an is close to L. And both terms are not precisely defined, but we all have fairly good intuitive feeling about what it is. Basically, you can think of it the following way. This is generally the same thing as the limit of just a real valued function in calculus 1, just domain is dotted. Actually, we have individual points. So here it is. Let me immediately address one kind of serious limit. And here is example. So calculate the limit when n goes to infinity, 1 plus 1 over n to the n. Fine, if it exists, the limit might not exist. Maybe there is no trend when n goes to infinity. But so find out if trend exists, and if it does exist, then find what it is. So generally what happens is, if you calculate these numbers, right, you calculate the first few numbers, and here is what is important and makes a difference from calculus 1. your domain are not all real numbers. So we have 1, 2, 3, 4, 5. So these are your just inputs. And then for each of them you calculate. When n is 1, n equals 2, n equals 3, n equals 4, n equals 5. So when n is 1, you will get 2. So values will be red. So there is a red dot here at 2. Let's say this is 2. When n is 2, it will be 1 plus 1/2, which is 3 halves. When you square it, you get 9 quarters. So you'll get more. And when n is 3, you will get 69. So 1 and 1/3 is 4/3. No, 4/3 to the cube, actually. Yes, 4/3 to the cube. So A3 is 4/3 to the cube, which is 64 over 27. So here is 64 over 27. That's a little more. And then when n equals 4, you'll get 5 quarters to the 4. It will be slightly more. It will be slightly more. But it looks that these values are stabilizing around some number. And that is actually the limit we would like to calculate. So is there some high, like horizontal asymptote, that these dots are approaching? So what we'll do here is basically, instead of analyzing our sequence, we want to use the machinery from Calculus 1. So what is the machinery in Calculus 1? In Calculus 1, we analyzed a real valued function going through these dots. Those are not the same object, but they are closely related. So what would that object be? So generally what we did here, we analyzed the following function, f of x equals 1 plus 1 over x to the x. Why do we like that more? Because now we have all the machinery from Calculus 1, we can do derivatives, maybe we can do L'Hopital rule, and so on and so on. So things, actually we have more options, and obviously the trend of the black line will also guide the red dots. So question is about the red dots, but this guiding line actually helps us to get the answer. So what are we gonna do? If you remember, we did that in Calculus 1. So instead of analyzing f of x, we'll look at the g of x, which is ln of f of x. And that would be ln of 1 plus 1 over x to the x, which is, according to the property of logs, x times ln of 1 plus 1 over x. And then we'll calculate the limit when x goes to infinity. And then this expression we will write like this, ln of 1 plus 1 over x over 1 over x. So we kind of thought of this over 1 and then divided up and down by x. Why? Because we wanted it to be kind of convenient for L'Hopital's rule. Now I'm quite tempted to do one little trick to kind of it would simplify very nicely our calculations, but maybe not actually. I was going to do substitution 1 over x to be u, and then u would go to 0, and expression would be much easier to differentiate. But actually, to keep connection with my red dots, I want to keep it at infinity, even at the expense of heavier calculation. So what are we going to do here? If we plug in x to be infinity, 1 over infinity is close to 0, very small. 1 and 0 is 1. ln 1 is 0 over 0. So we are allowed to use L'Hopital's rule. And that will be limit when x goes to infinity. On top, what do we get? 1 over 1 plus 1 over x, like 1 over u times u prime, which is negative 1 over x squared. On the bottom, we'll get negative 1 over x squared. And then what happens is it wasn't that bad. So these two guys cancel, and now when we plug in limit when x goes to infinity, 1 over infinity is 0, so we get 1 over 1, which is 1. So what did we get here? We got actually that the g of x is close to 1 when x goes to infinity. I'm writing it not in limit notation, more in informal notation, so this looks more like an equality. So if we raise it to both sides, we get e to the g of x is close to e to the 1 when x goes to infinity, but e to the g of x is actually f of x. So, where do I write it? I can write it here. So f of x is close to e when x approaches infinity. And let's write it now more formally mathematically. Limit f of x when x goes to infinity equals e. So now we go back to our dots. The same trend must be true for them as well. Limit when n goes to infinity 1 plus 1 over n to the n equals e. So this is important technology. I kind of started the lecture with a fairly heavy problem, not some trivialities where you just plug it in and see the result. Actually, we really need to pull out more serious machinery, and that was very often, if you want to use calculus machinery, then we, instead of our sequence, we actually look at the underlying real valued function when we get conclusions about that underlying function, and we get conclusion about our sequence. I'm not saying that we do this always, but very often this is an important technique. All right. One of the important techniques for calculating the limits is the same one that we've seen in calculus 1, and this is the squeeze theorem. Let me recall what that theorem says. So squeeze theorem says if limit of a when n goes to infinity equals limit of b n when n goes to infinity equals L. So two sequences have the same limits, and an is less than or equal cn less than or equal bn. So our sequence cn is between them, and that's where it's squeezed. N is between them. Maybe not for every n, for certain, from certain number on, index on. So that means maybe first 5, 6 might fail these inequalities, but once you start, you want to have it for the rest of the n's. Starting from 10, starting from 20, whatever it is, then Cn has no choice because it's squeezed between those two and must follow the same limit. And that's kind of nothing surprising if you draw it. If you say An goes like this, and then Bn goes like this toward the same limit, and then however unruly our sequence is, there is no freedom, actually it has to follow the same limit. It's common sense, and let's see how do we use it. So here's example. Find limit sine n over n when n goes to infinity. What's the problem with this sequence? So n steadily goes 1, 2, 3, 4, 5, but the sine n fluctuates because sine is periodic function, depends where you are in the period of sine. So sometimes it will be close to 0, sometimes it will be close to 1, so it's not easy to follow its behavior. But here's what we'll say, basically the same thing as in Calc 1. We'll say the following. We'll choose the squeezers. And who are the squeezers? An is negative 1 over n. Bn is 1 over n. And then what? Then conclusion is very easy. We know that sine n is always between 1 and negative 1. That's a well-known property of trig functions. So when we divide by n, which is okay because it's a positive number, negative 1 over n is less than or equal sine n over n, less than or equal 1 over n. So those are our squeezers. So here is left squeezer, here is the right one, and then what? Then what is the limit Usually I don't even write that, to be honest. Here's what I do. I just informally say minus 1 over n approaches 0 when n goes to infinity. This is a much more transparent way than writing. 1 over n also goes to the same limit 0. That's our L. So according to the squeeze theorem, sine n over n has no other choice but to go to 0. And that's it. If I were to write more of this instead of this visual, we would say since limit negative 1 over n when n goes to 0 is 0, and limit 1 over n when n goes to infinity is 0, and negative 1 over n sine n over n less than or equal to 1 over n for all n greater or equal to 1, according in mathematical statement to the squeeze theorem. We have limit sine n over n when n goes to infinity equals to 0. So here is the sentence actually describing this little diagram as mathematical statement. All right, so that's basically, so what are we doing today? Once again, we are discussing convergence of the sequences, very often relying on our intuition about convergence of functions. It will be even more obvious in the next problem, and next problem is, example, find the limit when n goes to infinity 5n over square root of n squared plus 4. What are we going to do here? This will be the same as basically the way we calculate it for the underlying function 5x or square root of x squared plus 4, because just common sense analyzing. When n gets big, this is obviously big, and this is also big. So generally, when you have big numerator in denominator, there is a fight of infinities. So what can we do? Just basically measure their strength. And who does that measurement? Powers of n. Which power should we use? N. So we divide by n, and n will expose how strong they are. So limit n goes to infinity 5n over n over square root of n squared plus 4 over n. And then we need a little careful algebra. 5n over n is just 5. Now what? In order to combine these two expressions, we need a little algebra. N is basically, will be rewritten as square root of n squared. Be careful, square root of n squared is absolute value of n. So if we are dealing with negative objects, we have to do it more carefully. But n is positive, so our domain are positive numbers, so we don't need to worry about it. And then what happens? Then, since I have two square roots, I can get them together. N squared plus 4 over n squared. And then, now we can split. Here is square root, n squared over n squared is 1, plus 4 over n squared. And then what happens when n goes to infinity? Common sense says that this is close to 0, so our limit equals to 5. 5 over 1. Just plug it in at the end. And that's it. So everything is here. By the way, if you look at our lecture notes, you can see that solution that I provided there is was done using squeeze theorem just to illustrate that theorem, but really I thought it's more honest if we do the simpler way than just, pretend that the fancier technique is necessary. All right, next problem. Something that we'll need actually quite often in the sections to come, and that question is, let an equals 1 times 3 times 5 times 2n minus 1. So it's product of first and odd numbers. And on the bottom, we have n factorial. and we would like to know what is the trend. Do these numbers, when I start calculating them, do they approach some value, or they are just approaching infinity? By the way, maybe sometimes when you don't have idea what's happening, our graphing calculator might help us. And in section 2, I will show you how to graph sequences and the object that we start from section 9.2, which is series, how to kind of analyze them using graphing calculator. Today we'll just do the abstract analysis. So what happens here actually, if you look at it a little, so this one is really more like common sense analysis than heavy machinery. Let me write here 1, 3 times 5 times 2n minus 1. And on the bottom n factorial, I write it as 1 times 2 times 3 times n. So when you compare the top and the bottom factors, obviously the top ones are bigger. But how much bigger? That's the question. Because they are bigger, that means it will converge to 7 or 9, or they are dominating by enough to make this go to infinity. And here's the main thing. All right, this guy is 1. That's nothing, fairly neutral. Let's look at this guy. It's 3/2. What about next quotient? Is it bigger or smaller? And it's quite easy to see that 5/3 are bigger than 3/2. And generally, whenever we keep going, we will see that each of these members is bigger than 3/2. So we can say the following. 3/2 is bigger than or equal to 3/2. 5/3 is bigger than or equal to 3/2. So if you cross multiply, you'll see 10 is bigger than 9. Next one hidden among the dots is 7/5 is bigger than or equal to 3/2. Generally, for any k between, 2k minus 1 over k is bigger than or equal to 3/2. So why is that? If that's not obvious, if you cross multiply, this is equivalent to 4k minus 2 greater than or equal to 3k, which is equivalent to k greater than or equal to 2. And that's exactly what we have. Our k starts with 2. So for all the members in between, 2k minus 1 over k will be greater than or equal to 3/2. And then the last one, k just generic one. The last one is 2n minus 1 over n is greater than or equal to 3/2. So what is that telling us? That this is greater than or equal to 3/2 times 3/2 times 3/2 k minus 1 times. Because first one doesn't give us 3/2, all the others, and there are n minus 1, sorry. And n is the total count, n minus 1 times. And how much is this? 3/2 to the n minus 1. And now it's quite obvious. This sequence obviously goes to infinity because it's exponential sequence. With the base is greater than 1, so those sequences go like this, although we just use positive part. It's exponential sequence, it goes to infinity. Since this goes to infinity and our sequence is above it, then that one will also go to infinity. So the answer is limit an is infinity. So we actually did some comparison. We said, oh, our members are higher than some members that are really getting huge, so our members are also getting huge. All right. Couple of more problems. That is actually one more important reasoning. So let me do problem number 60, similar to this one. Number 60 says n equals n minus 2 factorial over n factorial. This one actually just looks bulky, but this is something that we will also need quite often in this chapter. Here's what it stands for. N minus 2 factorial basically is from n minus 2 and then lower numbers, n 3, 2, 1. N factorial goes from n doing the same thing. So what happens now? You can see quite easily, basically, that they have tons of factors that they share. From n minus 2 on, they actually have the same factors, and we can cancel them out. So in the future, what I would like you to write this little more compact way. N minus 2 factorial. N starts earlier. N minus 1, and the others are exactly n minus 2 factorial. That's what we crossed. Now you cross them in a more compact way, one way or the other. It's 1 over n minus 1. And obviously, when n goes to infinity, you get huge numbers on the denominator. 1 over those big numbers approaches 0. So we get limit an when n goes to infinity is 0. So this was fairly simple. And one more problem where actually we just need to be careful. It's fairly simple. Number 62. We want an equals n squared over 2n plus 1 minus n squared over 2n minus 1. This problem has one important message, and that is when you have minus within your limit, you are only allowed to split if both those limits exist. So in this case, actually, if I were to try to split these two guys, that would be wrong. Because this limit is infinity and this is infinity. Why is that? Because obviously the numerator has higher degree than denominator. So what should I do actually? I should get them together and get common denominator, and then strength test will work. So limit an when n goes to infinity equals common denominator is 2n plus 1, 2n minus 1. First guy gets 2n minus 1, second one gets 2n plus 1. In order, instead of distributing there, I would rather factor out n squared to make it less bulky. Do it however you want them. So I get 2n minus 1 minus 2n minus 1. I distributed minus, they both became negative. How much is this limit? These two guys cancel each other out. So basically we get the bottom limit. When n goes to infinity, negative 2n squared. Here I can distribute and get 4n squared minus 1. So it's quite obvious now what will strength comparison give us if we divide by n squared minus 2n squared over n squared, 4n squared over n squared minus 1 over n squared. What would that be? Limit when n goes to infinity, we get negative 2 over 4 minus 1 over n squared. And obviously this approaches 0. So we just plug it in and get negative 1/2. So that's the limit. So this was, I would say, fairly simple. Just the main thing was don't try to split them, actually, quite the opposite. Get them together and then do the comparison. Here is one very famous theorem about convergence of sequences. That's not calculating the limit, but helps you to know if the limit exists. That's one well-known theorem. So the theorem says if a sequence is monotone and bounded, then it is convergent. By the way, condition monotone means increasing or decreasing, although it doesn't have to be from the first members. You can fail on the first few members because convergence kicks in only later on. So what happens with first 10 members, you can change them however you want. Convergence status will not change. And then, and for bounded, of course, it has to be bounded wherever you cut it. And then convergent means the limit exists. So here's one example, number 86. Show, so an equals n e to the minus n over 2. Show that limit when n goes to infinity, an exists, which means what? The sequence is convergent. That's what convergent means. Convergent. So, I just show, of course, we can choose it with the underlying sequence and using L'Hopital rule, but I wanted to illustrate what we just learned. So, so how do we prove that? First, so fact number one. What? First thing is, how do we show? So, show that it is monotone. I don't know, monotone might mean increasing or decreasing. So one of the best ways to show that function monotone is just to use derivatives again, not on the sequence because it's dotted, but on the underlying function. So f of x equals x e to the minus x over 2. So I'll see how derivative of this function behaves. F prime of x, so it's product 1 e to the minus x over 2 plus x times negative 1/2 e to the minus x over 2. When I factor out e to the minus x over 2, I get 1 minus x over 2. So what is that telling me? It's telling me that this derivative is greater than or equal to 0. No, it's less than or equal to 0. It's less than or equal to 0. For x greater than or equal to 2. Why? Because if x is greater than or equal to 2, x over half is greater than or equal to 1. 1 minus numbers that greater than 1 is negative or equal to 0. So what is that telling me actually? That, and then we say, but what happens with the first member? We said monotonicity is needed from certain member on. First member doesn't really matter for convergence. So from here we conclude what? That f of x is decreasing for x greater than or equal to 2. Therefore, an is also decreasing for n greater. So no matter what the first member is, and the first member is 1 to the minus 1/2, I don't even care what happens there. When I check second member here, then the other members are just lower than that one. So it is really decreasing. All right, so we showed that it's monotone. Is it bounded? What does it mean bounded? There are two numbers, so that the values always stay between those two numbers. And the answer is obviously yes. Why? Because since it's first, an is always greater than or equal to 0. Why? Because exponential function is positive, or n is positive, so an is greater than or equal to 0. And then it's less than or equal what? Whatever a2 is less than or equal. But we can say, again, what about a1? So a1 might be bigger than a2. I can put it in calculator and calculate, but if I want to just, that effort is really not necessary, we'll say less than or equal than maximum of a1 and a2. As I said, I can see who is bigger, but really it doesn't matter. So we say the following: calculate a2, calculate a1, whoever is bigger, that's your number that you stay below. So you are between two values. That's what bounded means. You are within a stripe. And if you are within a stripe and you're a monotone, my monotone is here is better. So if you are monotone and within a stripe, then you are convergent. So our conclusion is converges. And that's a famous theorem from mathematics. And then just one more comment. This is like more something that's a little exotic, and that is one interesting sequence. It's in the homework. It's defined recursively, and it's defined like this. So that sequence, number 121, is defined as an plus 2 equals an plus 1 plus an, where a1 is a 1, a2 is also 1. This is the famous Fibonacci sequence. So here, they didn't give us the formula, didn't express members as a function of n. Actually, they expressed members in terms of each other. So generally what happens, we can calculate them. A1 is a 1, A2 is a 1, A3 is the sum of the two previous members, so that's 2. A4 is 1 and 2, which is 3. A5 is 5. A6 is 8, and so on. And that's, this is a famous Fibonacci sequence. So what we are interested here is to actually see, so obviously it goes to infinity. But interesting question is, what happens with these ratios? So this ratio is 3/2, 5/3, 8/5. So let's say that Bn is actually an plus 1 over a. So what happens with this sequence? I don't know if the limit exists. Let's assume for a moment. Assume that limit exists. Nobody guarantees that. Assume that limit of Bn when n goes to infinity exists. That's not clear why, but I'll postpone that for a minute. If I knew that, then I can actually tell you what that limit is. Why? Because I'll do the following. Let's say that that limit is some number r. And then what do? I look at this connection. N plus 2 equals n plus 1 plus n. And I'll divide both sides by n plus 1. And we get the following. N plus 2 over n plus 1 equals 1 plus an over n plus 1. And now I'll take a limit on both sides. So limit here when it goes to infinity, and limit here when it goes to infinity. This is actually, what is this? This is the same as this, just one index later. So this is Bn plus 1. And this is 1 over Bn. So just the same quotient, just with the reciprocal. So generally, if Bn goes to R, then if I keep counting the next member, that's the same trend. So generally, this limit is just R equals. What about this one? Since I flipped members, these quotients, so if original quotient approaches R, then reciprocals approach 1 over R. And actually what happened is, I got quadratic equation that actually I can use to calculate how much R is. It's like a looping method in a way. So multiply by R, you get R squared is R plus 1, which gives me quadratic equation. R squared minus R minus 1 equals 0. R equals 1 plus or minus square root of 5 over 2. This quadratic equation has two solutions, but I only want one. Why? Because numbers are positive, so my ratios are positive. So if I use 1 minus root 5, that's negative, so it doesn't make sense. So I've erased this, and here is that ratio. This is, by the way, approximately 1.7. And what is this? This is one of the most famous constants in mathematics. It's called golden ratio. So this number here actually is golden ratio. And that's it. We calculated the limit. Once we knew that it exists, the question is, well, how do we know that it exists? Actually, if you write these ratios look like this. 1 over 1 is 1, and then it's 2 over 1, and then it's 3 over 2. I'm writing them in two different lines. And then it's 5 over 3. And then it's 8 over 5 here. And here would be 13 over 8. And actually what could happen, and that's fairly easy to show, this sequence is actually increasing. And this sequence is decreasing. And it looks like this. These upper quotients are below the ratio. So here is that ratio. So these quotients from here are increasing and approaching from below. And then the black ones are above, and they are decreasing and approaching from above. So if we call our theorem, we can say the following, but just for a bit, because there's no monotonicity for the whole sequence, but for the half sequence. So we can say for the upper half, upper half is here. Upper half is monotone, so increasing and bounded by the other members. Then there is a limit. And then this sequence is also monotone and bounded, and there is a limit. So each of them individually has a limit, and then their difference is obviously approaching 0, so they have the same limit, so generally that's the limit of the whole sequence. So generally limit of b2n when n goes to infinity exists equals r limit of b2n plus 1 when n goes to infinity is equals r. So limit for the whole sequence exists, and that's your r. This is a little more sophisticated example. Don't expect this on your exam or something like that. But I thought it's interesting to illustrate the power of that theorem that we just learned. And why is it good to know these theorems? Because without it, we would have real troubles showing that this limit exists. And also, it's part of mathematical culture to be aware what Golden ratio is. By the way, there are big stories about Golden ratio in arts. People consider that that's the most pleasing rectangle is the one that has Golden ratio. So if this side is 1, then this one is r, which would be 1 plus root 5 over 2. So that's considered since the times of Aristotle that basically this rectangle is ideal because it's neither too wide and neither too close to a square. So that would be most aesthetically pleasing, and you will see, for example, frames of paintings, formats of paintings, especially in the traditional art, are very often having Golden ratio. So artists are always aware of this ratio. So I'm glad we saw it how it comes out of Fibonacci sequence.